Today we're going to talk about gravitational redshift. Gravitational redshift. First of all, let's talk about Doppler effect. Doppler effect says if you have a source A that emits light frequency omega 0, then you have observer B, which is moving towards source A at a speed of v. If v is much smaller than light speed c, then the frequency received by observer B is omega 0. The frequency observer B received is higher because the time period it takes for observer B to receive each subsequent light pulse is shorter, since observer is moving closer to A. That's why the frequency is higher when observer is moving towards source A. Now, let's look at another case. Case 2, in deep space. Deep space means in the space where we are so far away from anything, so there's a zero gravitational effect. So assume we have a rocket in the deep space. Rocket is just flying, and so the rocket is moving with acceleration. Let's say acceleration magnitude is g. Inside that rocket, if we have two objects, one is A, another is B. Let's say A again emits light at the omega 0. And what would B has to receive in terms of frequency or observe? In this case, when the light is emitted from source A inside the rocket, at the moment the light left source A start traveling towards B, B had the same speed as A. But since the entire rocket is accelerating, and before the light actually reach B, B already gained additional speed. Let's assume the distance between A and B is h. The light travel from A to B, it will take time, and that time you equal T equal to h over c. You can argue that actually time may be slightly less than that, because B is moving while C is traveling towards B. B is moving upwards relative to A because B is gaining speed. But the distance that B gaining over that period of time T equal to H over C is relatively small compared the distance light travels, because light speed is so fast, and the additional speed B has gained is delta V equal to gt. Okay, over that period of time, the acceleration is g. Over that period of time, the additional speed gained by B is gt. So with those two, we can say that according to Doppler effect, omega 1 received by the observer B is equal to omega 0 and 1 over V trace C. In this case, V is delta V between A and B, because both A and B are accelerating, but B will gain additional speed gt over the light traveling time t. So this should equal to omega 0, 1 plus delta V is g times t. Okay, g times t. T is h over c. Then you have this c squared, be a delta V over c, and t equal to h over c again. That's why this is the new frequency. You can see that observer B in the accelerating rocket in the deep space is increased when observed by the people on the floor of the rocket or the back end of the rocket. Okay, now let's look at the third case. Let's look at the rocket on Earth. Or in fact, it could be just a high building, okay, on Earth. It doesn't matter in this case. Assume this building is at rest on Earth. Because on Earth we have a gravitational field, the gravitational field G. According to Einstein's principle of equivalence, the rocket in the deeper space with acceleration g is exactly equivalent with a rocket or building at rest on Earth for the observer inside this building or inside the rocket in deep space. So if I have a emitter A in that building that again emit light at the frequency of omega 0, I have observer B at the bottom of the building try to receive the light. This is Earth's surface. So in this case, if the height again between these two objects is h, then Einstein's principal equivalence should tell us all optical phenomena by the observer should be the same. That means omega 1, which is the frequency observed by B, should again equal to omega 0 plus 1 over V over C. And in this case, omega 0, 1 plus GH over C squared. So here the V is hard to tell what is it, but if you look at equivalence, omega 1 is determined by the gravitational field and the distance between two objects and over C. So this V is equivalent V in case 2 in deep space. That's the relative speed gained between A and B due to the acceleration of G. In this case, you can say due to the gravitational field of G. So what does it tell us? This tells us omega, the frequency at the bottom of the building is higher than the frequency when the light is emitted from the top of the building. Reversely, that just means omega, if we have a light source emitted from B and go to A would observe a frequency that would be smaller. Let's say A would observe a frequency emitted by B, so that would be smaller. Okay, and a light source emit a frequency from B. When I go to observe A, the frequency is small. So those two are the same. So when frequency is smaller, means wavelength is bigger or longer in this case. The wavelength received by A at the top of the building is longer than the wavelength at the bottom of the building. That's we call redshift, because longer wavelength is redder in spectrum. Shorter wavelength, high frequency is bluer. So that means inside the gravitational field, you go higher in altitude, your wavelength will be longer and redder. You keep going higher, your wavelength being longer and worse. So the further away you are from Earth, the longer the wavelength will be. This is the gravitational redshift.